All right, ladies and excuse me. All right, ladies and gentlemen, how are we today? Here we are going to be talking about Monte Carlo, using Monte Carlo simulation to make hard reliability analyses. Excuse me, easier, and it actually is. I mean, it sounds very intimidating, especially Monte Carlo simulation. This or in that, and we see in university textbooks and university, well, papers, I should say. Yeah, and we solve this problem using Monte Carlo simulation. And I'll reference it a lot. And as Fred mentioned, I've always been told, okay, just show, if it's that easy, show us how to do it. And it actually really is it really is, can be, well, it is easy. And hopefully my aim is for the end of this conversation today for us to be in furious agreement that this is actually a lot easier than it sounds. And so let's set the scenario that we're trying to maybe get on top of where Monte Carlo simulation can be helpful. Here is what looks like here are what looks like two parallel pumps. And the reason we want parallel pumps is because they offer redundancy. One pump is going to be able to take over the role of the other pump when the other pump fails. And that extends reliability. Now, we can be really clever about this and extend it even further if, for example, a switching system makes sense. The idea of a switching system is that we now have a valve at the upstream of both pumps. The idea is that once something is detected wrong with the primary pump, then the valve can simply say, okay, I'm going to switch over to the standby or backup pump. Now, the reason why you want to do that is if in this scenario, isolating that standby or backup pump allows that pump to last for a lot longer. So if we essentially mothball that pump while it's in standby mode before it's being used, we can it essentially sits there accumulating precious little damage, and it means it's more than likely ready to perform with most of its residual useful life ready to go. And that is only going to happen if we have that switching valve. But there's some things we need to be aware of, and that is even if this is in a mothball or standby scenario, we still need to understand if that pump is still working if it's somehow survived that standby mothballing, let's call it that. And of course, the valve itself can fail too. It's not going to be 100% reliable. And so for this system to allow that backup pump to work, we need to ensure essentially that the switching valve is still working at the time the first pump fails. So the switching valve cannot fail before the first pump fails, and the backup pump can't fail before the first pump fails in order for us to use it. And of course, if we now are doing this, it means that the reliability characteristics of each of these components becomes a little bit more complex. We actually have two reliability equations for the backup pump, for example, because we have a reliability or function, I should say, reliability function for it in the standby mode and a reliability function for it in the operational mode. And because this is complex, let's have a look at the equation that describes the reliability of this system, of this what we call a switching system. Don't know why that's hard to get out. That's the equation right there. And there are lots of valid responses to this equation. Vomit, hallucinations, nausea are the usual ones. That usually means that you're actually fit and healthy, because this is not a fun equation to solve. And so what usually happens is that people use this thing called an approach called a perfect switching system. Has anyone heard of a show of hands? Who's heard of a perfect switching system? Anyone heard of it? Got a small number, really small number of you have heard of what's called a perfect switching system. Anyway, long story short, we see the term perfect switching system a lot, especially in textbooks, because one of the only ways you can even come close to analyzing this equation is if we assume one, the valve doesn't fail, two, the backup pump doesn't fail while it's in standby mode, which makes this switching system perfect. And so we often have the equations for the perfect switching systems because as opposed to that equation, which should make you go, wow, you can, with some additional assumptions, start to solve or model that perfect switching system. But there is a much better way to be able to model or essentially evaluate that equation we just looked at for that real world switching system where the first pump will fail when it fails. The switching valve itself can also fail. And the reason we're doing this is to isolate the standby pump, which means it's going to fail in different ways in the standby and operational mode. So if we're going to be serious about modeling it, we need to model the reliability of that pump in two different ways. So there is a better way. But before we do that, really come to terms with this better way of modeling the system, this switching system, we're going to do what is for some revision, and what is for the rest the basis of the Monte Carlo approach we're going to start touching and looking at later on. So here's a ball bearing, one of my favorite systems / components of all time. Beautifully designed system. It's called a system, component, item, product, whatever. It's a really sophisticated design, a ball bearing. And we know that failure is a random process. If it wasn't a random process, there would be no such thing as reliability engineering. And we also know that because failure is a random process, seemingly identical ball bearings have the nerve to fail at different times when used in seemingly identical ways. And these seemingly identical ball bearings, even though they look identical to us, we know have differences. So we know the one on the left, oh, that's a random arrow sticking up there, good Lord. One on the left, even though it looks identical to the one on the right, we know that it could have an impurity in its inner race, while the one on the right, it could have a dislocation on its outer race. And we know that these microscopic defects and changes exist. So we know that even though we call these things identical, they're not truly the same. And perhaps we use the term identical when instead we should be using the term indistinguishable. And it's all these teeny tiny little changes in the way our ball bearings experience the world around them, which means that, again, seemingly identical ball bearings will fail at different times. And the random hand of failure is my way of representing all these factors and all these uncertainties which make seemingly identical ball bearings fail at different times. So if we add beneath our random hand of failure, this arrow here, this axis, which represents time to failure. And for ball bearings, time is measured in terms of cycles or revolutions. And for your system, time is essentially analogous to how we measure the age of your component, product, system, item, or whatever it is. And it's very important to get that right. And us using the word time in time to failure is not of itself a problem, because in the reliability engineering industry, it's well known that time to failure can be measured in terms of cycles, revolutions, distance, operating hours, calendar time, whatever is the best way to measure the age of your system. And so this random hand of failure essentially governs or which represents the different ways things can fail, is going to be responsible for essentially us seeing these blue data points which represent different times to failure of different ball bearings, in this case 100 ball bearings. But just because something is random doesn't mean it's not predictable. We can see straight away, for example, that the data points are clearly denser over there. They're more tightly packed within the region I've circled. So we know that our ball bearing is more likely to fail in this region of time to failure. And so that's really, really interesting. It's really helpful, but it isn't easy to see density with these data points like this. And so because humans are very visual creatures, our subconscious brains are the ones that deal with randomness and uncertainty. Our conscious brains, which are very good with visualization and things like that, hate uncertainty. Our conscious brains love the fact that 2 plus 2 equals 4. Our conscious brains would love the rest of the world to act that way, but unfortunately, failure is that random process. And so we can use, for example, a histogram. Oh, come back, histogram, with these different bars to represent the data frequency or approximate likelihood of these times to failure. And this histogram is starting to better visualize the nature of the random hand of failure, the different ways, the different likelihoods associated with times to failure, which essentially are the signature of a random process. And even though this histogram is useful, it's still not very, very smooth to help us get a true picture of the underlying process. And it's one way of smoothing out this histogram is to get more information. And so, for example, we could go and test, in this case, I think 1,000 ball bearings until they failed. And now you can see the histogram is clearly much smoother with a clearer pattern. But of course, there's always a level of roughness with this histogram, no matter how many data points we add. So let's just say we add an inconceivably high number of data points, million, billion, trillion, whatever word you use as a kid to represent something that is truly huge, a gigabillion, whatever it is, an incredible number of data points, i.e. something that's not realistically measurable. But if we were able to measure an incredible number of data points, our histogram would collapse to a beautifully smooth shape. And that's what it would look like if we had a huge amount of information or data. Perhaps we can call this the ultimate histogram. This ultimate histogram is great for us primitive human beings who really want to be able to visualize stuff, because this smooth shape represents the likelihood of time to failure having a specific value. And we can see that this ultimate histogram shape indicates where it's most likely for time to failure values to exist. And that's really, really useful. And of course, this is but one way of looking at data. So for example, we could look at this in terms of reliability. All I've done here is got exactly the same data points, and I have added a vertical axis to give us an additional dimension, additional visual characteristic to the data we've collected. So the time to failure values for each data point hasn't changed, so that the X value hasn't changed, but now we've added a Y value, which is based on the percentage of things that are still working. And this is really useful because this allows us to draw a smooth reliability line if we have an incredible amount of data. And that allows us to, for example, to work out where the B10 life is of our ball bearing. Essentially, the B10 life is where reliability drops to 90%, or in other words, where we would expect, when we would expect the first 10% of our ball bearings to fail. And so the reliability curve is really, really helpful for us to actually get numbers to make decisions. The ultimate histogram shape, that orange thing in the back, sometimes we call it the probability density curve. Some people, perhaps somewhat incorrectly, but I know what you mean, you call that the probability density function. But the shape in the back helps us visualize where time to failure is most likely to occur. But the blue line, the reliability curve, is really helpful for us to get actual numbers to help us make better decisions. And so let's get rid of all but 100, or I think 50 data points. And so you can see here that I've left the reliability curve there, that blue line, I made it thinner. And so it's just a little bit more crisp. And you can see that I think we have 50 data points here, and hopefully you would agree with me in that they look like they are spread in accordance with the shape in the background. I know this to be the case because I asked my computer to generate these data points before we started. So I know that when my computer was simulating these data points, it was using that ultimate histogram shape in the back to create or work out the horizontal displacement of these blue data points. But I'm going to show you something which is very, very crucial for the rest of today's conversation. And so if you haven't been paying attention up until now, I highly recommend you switch on for what's about to happen and pay close attention to your screen. Because what we're going to do is we're going to draw lines straight up from each data point and have those lines hit their reliability curve and have that reliability curve, and when it hits a reliability curve, then draw a line straight to the left. Now, why am I doing this? What we are observing right now is when we go through this process of drawing a line up from each dot, hitting the reliability curve, then turning left across the vertical axis. So essentially, we're finding the reliability value of each data point. Statistically, what we are doing is creating, where those lines intersect with the vertical axis is always, and I mean always, uniformly random. So even though we can see the blue data points are clearly not uniformly random across the horizontal axis, you can see they're clustered in a certain region. As soon as we draw lines up from each data point, hit the reliability curve, do a left turn, and see where that line ends up on the vertical axis, where the line hits the vertical axis, that point of intersection for all the data points is uniformly random or uniformly spread from 0 to 100%, even if the nature of our failure changes. So for example, this is how a ball bearing fails. Let's look at this approach or these data points when instead of looking at how a ball bearing fails, we look at how something like a rubber tire fails, which fails when enough tread is worn away at a uniform rate. And for those who've been in previous webinars of mine, you might automatically know that that is the ultimate histogram shape that describes that failure mechanism is a bell curve. But you can also see that the data points in terms of the lines they've created have not changed at all. Of course, as they now cluster in different regions because the ultimate histogram shape has changed because it's a different failure mechanism, where those lines intersect with the vertical axis hasn't changed at all. They're still uniformly spread from top to bottom. And this is a very important feature of any random process. If you were to have a reliability curve for any random failure process, and you're able to measure the data points or the times to failure and plot them on a chart like this, every time you draw a line straight up from those data points, hit the reliability curve and do a hard left to the vertical axis, where those lines hit the vertical axis, they're always uniformly spread from top to bottom. And of course, the spread is not perfect in that they are not equidistant apart, but because we're still doing it with a random process, you always see some clustering here or there. But the overall tendency, the random thing we're seeing is that they are uniformly spread from top to bottom, and that is going to help us a lot. Because essentially that means that the random hand of failure, whenever we ask a computer to simulate, all it does is essentially find those points based on starting with randomly selecting a point on the vertical axis and essentially going the other way to get those data points. And so you can always see that we always uniformly randomly spread when we have this little this little graphic, this little animation, this little approach. Draw a line straight up, hit the reliability curve, turn left, as intersection points, always uniformly random spread. And now we have the building blocks to start simulating random variables if we know the reliability curve. So if you know the reliability curve of something, you can simulate a random variable. And remember, part of the title was Monte Carlo simulation. So this is where the simulation bit comes from. So here's our random hand of failure. And let's just say, here's the reliability curve we have got from some process that we have measured in the past. In this case, this could be the reliability curve for our ball bearing that we know very well through study analysis or whatever. Now, when it comes to reliability curves, we tend to focus on the horizontal axis first, i.e. some point in time, draw a line straight up, and the height of that line is the reliability, which is driven by the reliability function. T is the input, the reliability function, and the output is the reliability. So in this case, about 66%. And so this is the sort of basic way we look at this in all charts. But what we need to do is look at it from a different way. Same reliability curve, but instead of starting with a point on the horizontal axis, start with the vertical axis. Now remember that to simulate or to generate a random variable, we have these values which are uniformly randomly spread on the vertical axis from 0 to 100. So here's a point, and let's just say we're going to simulate randomly select. Oh, there we go. So that blue cross has moved to a point which is uniformly randomly spread, and it is at a value of X. Now, if I was to draw a line from X across to the reliability curve, that distance there is given by the inverse reliability function, which you see has, instead of it being R followed by brackets, it's R with -1 as a superscript, R to the -1 or a power of -1. That's just a way of representing that this is, in a way, a function that goes the other way around. It just finds the same curve or describes the same curve, but instead of starting with a t to get the height, we start with the height to get the t. And this might seem like unnecessarily painful and unnecessarily torturous, but this is one of the first things we need to do when we start doing Monte Carlo simulation. The reason being is because when we do that, which is essentially what my computer did to simulate a single random variable, we are going to start with finding a random number between 0 and 100%, draw a line across, draw a line straight down, and that is simulated random variable number 1. And if we repeat that process over and over again, allows our computer to give us all these wonderful data points that you can see, create the histogram that gives rise to this reliability curve. All right, so how can we use this to make stuff happen? Let's go back to that switching system, which, as you know, is complex in that for this system to use a standby pump, when the first pump or primary pump fails, the switch cannot fail before the primary pump does, and neither can the standby pump. And the way each one behaves is very different depending on its different operational states. And so for us to fully understand this system, we really need to have reliability curves for each component. And for our standby pump, we need to have at least two reliability curves, one for reliability in the standby mode and one for reliability in operational mode. And the idea is the reliability curve for this in the standby mode should be a lot higher for a lot longer, because that's why we're doing this. We're trying to protect it. All right, now for some Microsoft Excel action. So what I'm going to do right now is I'm going to stop sharing ever so briefly so I can start sharing something else. So don't panic if you can't see anything right now. We're going to look at a spreadsheet. And I'll just ask someone to give me a thumbs up when you can see this spreadsheet come up on the screen. All right, there we go. We're good. So what I'm going to do is start doing some Monte Carlo simulation. Now, I'm just ad-libbing here, so hey, I hope you embrace amateurism. So, and I always like labeling things when it comes to pumps and anything else in spreadsheets. So column number one, column A, I should say, I'm going to write simulated time to failure for primary pump. Okay, so that's clearly That text up there is a bit too long for the cell, so I'm going to format cells. I'm going to allow the text to be wrapped. Okay, and all of a sudden we can see that at the very top, we have a title for column A. So let's just say that for pump A, we have understood that it's time to failure is modeled with a normal distribution with a mean of 10 and a standard deviation of 2. Now, the formula is about to see, I'm about to use, are going to be shown once we're done. So you don't have to memorize everything. But to make things, again, a little bit easier, I'm going to add parameter 1 in this row and parameter 2. So normal distribution, first parameter, the mean. We'll make it, make all this centered to make it a little bit easier. And a standard deviation of 2. Now, if I wanted to simulate a time to failure, so I can use the inverse reliability function or CDF function, and trust me, it works CDF as well, that's already built into Excel. And that is norm.inverse. Now, for probability, this is where we randomly select between 0 and 1 or 0 and 100%. Excel has a function called rand, where you have to put 2 brackets afterwards, which will randomly sample between 0 and 1. The mean, you're going to make 10 or whatever's in cell B2. And standard deviation is 2, which is in cell B3. Close brackets. And now you can see that we have a number which appears here. Now, when it comes to simulation, this is a completely simulated number. It's 11.408, so 11.48 hours. Now, if I ask Excel to recalculate, I can hit F9 or hit this icon up here, you'll see the number changes. And every time it recalculates, that number is being resampled in accordance with the bell curve defined with a mean of 10 and a standard deviation of 2. Okay, so there's simulated time to failure number 1. So we're going to do simulated time to failure for the switching valve now. Time I change anything in the spreadsheet, everything gets recalculated. So if I enter something in a new cell, you'll see this number changes here. I'm going to use a log normal distribution with a log mean of 2.5 and a log standard deviation of 0.1. And I use a very similar type of function, but instead of using norm inverse, I use log norm inverse, where I use these values up here. And now I have 2 simulated random variables. And every time I recalculate, you can see the numbers change. Now I'm going to add in this column here, did the valve fail before the primary pump? And all I need to do now is go, if that is less than or equal to this, if the time to failure for the valve, simulated time to failure for the valve is less than the simulated time to failure for the pump, then I'm going to put a big yes here. Otherwise, I'm going to keep it empty. And so you can see here that every time I calculate, you should see eventually, there we go, yes. In this case, in this simulation, yes, the valve failed before the primary pump. So this means that the system can't switch to the backup valve once backup pump, I should say, when after the first pump failed. So you can see simulating. Yes, every now and then the switching valve is failing before the primary pump. All right. But it's not just that. We now need to simulate time to failure for standby pump in standby mode. So we need to now also see if our standby pump is still working when it comes to switching across. Now, I'm going to use the Weibull distribution just to show out of the possible. We're going to have a scale parameter of 30 and a shape parameter of 5. And this actually generally has a time to failure, which is a lot longer than the other two times to failure, which you'd expect because we're trying to keep this simulated standby pump, I should say, protected. So unfortunately, Excel doesn't have an inbuilt Weibull inverse function. So we need to go old school and write it from scratch. And I'll show you these equations. But the main point is I'm trying to convey that it's possible for you to randomly simulate normal, log normal, and Weibly distributed random variables. And so the equation that you need to use involves getting the characteristic like the scale parameter and multiply by that the negative log of a random variable, which we randomly simulated reliability in this case. Line of 3. We'll do that. Hopefully we got the number of brackets right. Please work. And there we go. And you can see now that in this simulation, as you'd expect, the simulated time to failure for the pump in standby mode is now a good deal higher. And every time we recalculate, you can see that every time we simulate, there's a chance. It's a strong. The time to failure for the pump in the standby mode is usually pretty high, so there's a good chance that the standby pump won't fail before the primary pump does. Instead of the valve, we'll put now we can easily do the same thing. Equals if the simulated time to failure for the standby pump in standby mode is less than the simulated time to failure for the primary pump. Let me put a big fat yes here. Otherwise, and so every time we simulate, you can see here's a chance here in this case. Just so happened that even though it's highly unlikely, it is possible for the standby pump to fail in the standby mode before the primary pump fails. Now, we're not done yet because we need to simulate time to failure for standby pump in operational mode. And I'm going to make these characteristics of this standby pump in operational mode exactly the same as the characteristics for the primary pump. If they're the same pump, hopefully they work in the same way. So I'll just change the column, and here we go. So we're still not done because we now need to find simulate the overall time to failure for our system. We've got some rules here. We know about these rules. So simulated system time to failure. Let's make that bold. We know that if the standby pump fails before the primary pump fails, or the switching valve fails before the primary pump fails, then our system fails when the primary pump has failed. So if we go, any of these two cells here, which are about things failing first, either of those two are yes, then our system simply fails when our primary pump fails. Otherwise, our system fails after our primary pump fails, and then our standby pump fails in operational mode. So we add these two times together. So B4 plus G4. And now, sorry, my mistake. And now we have the simulated system time to failure. Now let's have a look at what's going on here.
Well,
We'll
hang
make
on.
this.
Take a look at that again. It looks like you used two logic ones for D4, and one of them should be
Oh, yeah.
F4.
Correct. Thanks, Fred.
Yep.
Good pickup. Thank you.
I'm paying attention, you know.
Killing it. Like I said, this is ad lib, so things can go wrong. Okay. So you can see here we have a simulated system time to failure. In this case, our valve did not fail before the primary pump failed. The standby pump did not fail before the primary pump failed. And so the simulated system time to failure is simply the simulated time to failure for the primary pump, 7.3-ish, plus a simulated time to failure for the standby pump in operational mode, 11.2-ish, which gives us 18.5. Now, every time we recalculate, you can see eventually we're going to have, there we go, the valve failed before the primary pump. And when that happens, our system fails exactly at the same time our primary pump fails. And so if you can understand this conceptually, then this is Monte Carlo simulation. Now, this is all good by itself, but we really need to do a little bit more than this to understand sort of the total characteristics of our system. So what we're going to do is ask Microsoft Excel to do this a lot. And when I say a lot, let's just say we're going to ask Excel to do this 1,000 times. Or actually, before I do that, I'm going to freeze panes here. Go down to cell down through and fill down. And essentially, Excel is now doing this a lot, 1,000 times. So why am I doing this? Well, that means I can, for example, select all the values in column H. Let's do that again. And I can insert a histogram if I want to see the characteristics of time to failure. And there's our histogram. You can see that histogram in this case has a couple of peaks. And that tells me that the first little peak on the left is almost certainly going to be down to the scenarios where the the valve or the standby pump doesn't work so that we cannot switch. And so the first little peak is down to first pump time to failure. But most of the time, the system switches successfully to the backup valve and we get this backup pump and we get this second peak over here. And every time we recalculate, we get a slightly different histogram, which is hopefully something you find very useful. Now, that of itself can be helpful, but let's now say we want to see the reliability curve, and we can do that by essentially adding a couple other columns over here. So we're going to go to ranked system time to failure. We're going to go, add the smallest number. Sorry, I need to add an index. Bear with me. So again, rank these from smallest to largest, where the index number 1 represents the index of the smallest value. And as you can see, Excel's going crazy. Every time I do something, it recalculates. Oh dear, come on, Chris, you're better than this. 4 plus 1, and then we're going to have the ranked system time to failure. And all we're doing is we're going to find the smallest value in our array over here, which is I4. Going to make sure when I fill down, things don't go crazy. And you can see that we're now starting to, bear with me for 1 second. And now we can see we have the ranked system time to failure over here. Every time we simulate, see that now the times to failure that are simulated are now ranked from smallest to largest. Now we can estimate the CDF at that point in time. which is going to use the median rank approximation. I have lots of other webinars on this, but I know I'm getting a little bit, actually got 1,001 data points here. So going to fill it down here. Now we have the CDF estimate. Now I can add a chart which shows the CDF, approximate CDF of our, let's see what we get. Here is our approximate CDF for our system based on our Monte Carlo simulation. And it's whenever we have a CDF or reliability curve, it automatically makes it that much smoother. So every time we re-simulate, you can see the curves, everything changes ever so slightly. And of course, sorry, Sean's asking a question. Is that histogram of times to failure for the entire switching system? Absolutely it is. And so you can see that we have a very complex system that we're starting to model with Monte Carlo simulation. But you can see every time we simulate, the things change. And we don't want that. They're not changing too much, but they are still changing. One thing we can do to mitigate that is simulate an incredible number of times. So let's go nuts. And instead of having 1,000 simulations, let's go to 10,000. And that's where Excel can sometimes slow down just a tad. Let's see what the art of the possible is. So we now have, I need to correct a couple of equations. We now have, instead of 1,000 data points, we now have 10,000. So let's fix that up. You can see Excel is taking a hell of a long time to update as a result. Instead of having 1,001, we have 10,000 on the nose. So let's try that. And of course, both these charts are now out of whack because they're only focusing on the first 1,000 data points still. So let's fix up our CDF, which instead of going to 1,004 goes to 10,003. See how that looks like. And there's our fixed up CDF. Now we need to, for our histogram, we now need to reselect the data. Instead of going to 1,004, goes to, oh my goodness. Let's see what our histogram looks like right now. So you can see our histogram is now much better formed, and every time I recalculate, firstly, it takes longer because Excel's going through 10,000 simulations, but the changes every time I resimulate are much less pronounced. Now, on the histogram, you can much better see those two humps starting to appear. The first little hump represents the scenarios where the system fails when the first pump fails. And the last hump represents the scenarios where the switching valve allows the standby pump to work in its operational mode, which happens most of the time, which is why that second hump is much bigger. And you can see that the CDF curve on the right-hand side, which we'll label a little bit better in a tick. You can see we have those two different regions. The first little region here where the system fails and the first pump fails, and the second region where the system fails when both pumps fail. And so what we can do is, especially for the CDF curve, we can go change the title to switching system failure probability. We can change the vertical axis. We'll make that so it goes to 1, not 100, not 1.2. We can make the number percentage. We often like percentages. Have 0 decimal places because we don't need that. And all of a sudden, we're starting to get a chart which is becoming much more useful. We can either label the chart. So let's add a chart element. Axis title. This is time to failure here. We'll add another chart element. Axis title, primary vertical, and that becomes CDF or F of T. And now, with this incredibly complex system, we now are relying on Excel to do all the hard work to come up with this CDF curve, which doesn't change very much at all anymore. And now from these numbers, you can relatively easily calculate things like the L10 life of your system. I see another question coming through. Is there an effective method to determine the number of simulations required based on desired confidence level? I'd argue there is no effective method, and the reason being is that it all depends on what metric you're trying to measure. So, for example, Kevin, if you're trying to find the median or estimate the median time to failure, you can do that with a lot more accuracy using Monte Carlo simulation than you can with finding when the first, for example, 0.1 of 1% of things fail. And the reason being is because the extreme values tend to be the ones which experience the most variation. So you need an incredible number of data points to be really, to get a really good understanding of when the first 0.1 of 1% of things fail compared to when understanding when the median occurs, when the first 50% of things fail. There's a lot more data each side, so to speak, of that metric when it's a 50th percentile versus the 0.1th percentile. And so it's a little bit of experience. It's a little bit of statistics as well, and often it can be quite as simple as working out how many times or what happens when you hit this button when you're trying to find a particular metric. So, for example, if I drag my window across to the right, I'm going to add another column called estimated L10 life, which is when I expect the first 10% of my things to fail. And one way of doing that is using finding the percentile, using the percentile formula. Again, I'm going through lots of formulas today. I know, where we are asking a lot from you guys to remember. I get that, but it's more or less showing what the art of the possible is. And if I put 0.1 here, this equation on the right-hand side tells us what the 10th percentile is of our simulated system times to failure. So in this case, the estimated L10 life is 12.6%, 12.6 hours or whatever the usage metric is. Now, if I resimulate, so remember it's 12.633 now, it's 12.66 in the next simulation, it's 12.63 again. So you can see it's still hovering 12.63, 12.66. So it's still 12.62s. Now, Kevin, if all you need to do is demonstrate that the L10 life exceeds 10 hours, then I think we're good, because we've got a lot of simulations, and every time we hit the button, the numbers hover between 12.62 and 12.66. So you can say with some confidence that the L10 life is greater than 10 hours. However, if the requirement is 12.6 hours, then even though it suggests that it is higher than 12.6 hours, it's a little bit close to comfort. So maybe there is scope for, oh, there we go, 12.57 from this one. So if the requirement is 12.6, maybe we need to do some more simulations to get the level of confidence. Now, confidence is a measure of you, it's not a measure of the system. So it's completely down to what it is, what questions you're trying to answer. Now, before we go back to PowerPoint, do we have any questions on what wizardry I've just, or what nonsense, let's call it by the right term, what nonsense I've just gone through before we move away from this Excel spreadsheet? Are there any questions? And that also allows me to take a little drink. No questions. Or these questions are so long, and I haven't given you enough time to finish typing them. Can see that Kevin has written that Minitab has Weibull and a bunch of others in it for random data. That's cool. I'm not sure if Minitab does inverse Weibull. I think it does, but Excel does. Excel certainly does Weibull, has Weibull distributions in it. It just doesn't have the inverse Weibull. No worries. Okay, thanks, Kevin. So in the context of Monte Carlo simulation, what decision are you trying to inform? And usually there is a number you're trying to see if the simulated number is greater than. Just simulate over and over again. If it's consistently higher by a long way, then we're good. You can see that, and I have a pretty powerful computer, but even with 10,000 simulations, Excel can take a little while to get through, chug through, and a lot of the time actually is devoted to ranking the system times to failure. All right, team. So bear with me. So that was an overview of Monte Carlo simulation in Excel. And the formula I used are on the screen right there. So if you need to screenshot them for use in the future, there they are. And hopefully you've seen what the art of the possible is when it comes to Monte Carlo simulation. Now, to become a master, or at least very competent, you can't just turn up to a webinar and take it all in matrix style and say, no worries, I'm good to go. You need to go and practice a few things and make lots of errors. Trust me, if you think I'm slick at this now, it's because my slickness is a function of the number of boneheaded errors I've made over the years when I've tried this myself. And so if you want to do this yourselves, you really need to practice and develop your skills in your own time. But hopefully you've seen that this is actually quite helpful to, especially when you have a system whose analytical reliability equation is mind-bogglingly challenging to understand. If you can wrap your head around simulating times to failure and just having those rules we looked at, then you can actually get some really useful outputs and have an incredibly complicated CDF function or histogram or estimated L10 life based on just simple repetition and allowing Excel and your computer to do all the heavy lifting. You can see that Sean writes, to answer Kevin's question, my experience, Sean's experience has been to use, where's that thing gone? Have you used trial and error to find the point at which additional iterations do not change results of the simulation, meaning that you are close enough to the perfect histogram. And that is also a good way of doing it. As a rule, though, what you need to do is you need to add roughly the same number of simulations you've gone through to see if there is a significant change. So, for example, if you have 10,000 simulations and you want to add additional simulations to see if there's a fundamental change, you can't just add one more simulation, because one more simulation is going to be eaten up by the 10,000 simulations that have already been gone through. If you want to see if more simulations will change it, as a rule, you need to double the number of simulations. And if doubling the number of simulations doesn't change much, then it's evidence to suggest that you're good to go. Kevin writes, he's played with Monte Carlo simulations a bit, not enough. It is a great way to get that feeling of, do I know anything? Yeah. Yes, as is being married and having children. Usually I get negative responses to those questions, unfortunately, especially from my children these days. Any more questions about what we covered today?
There's one over in the questions tab. Manthus is asking about
Oh,
copy of the slides or a copy of the spreadsheet that you just created.
I don't have access to the questions for today. Question tab. I don't know why.
Well, there was only two, and
Oh,
can we
there it
get a
is,
copy
Q&A.
of the slides and get a copy of the spreadsheet?
All right, so today, for the slides itself, I can certainly make the spreadsheet available. That's not a problem. For the slides, I was going to propose that I just simply use these equations here. If the slides want to become available, of course, my slides don't lend themselves to simple PDFing, Fred. I might have to put them in a little guidebook as per usual. But yeah, I can certainly make this spreadsheet available. In fact, I can even save it right now. And then add it to the chat while I'm talking.
Yeah.
Now I can't multitask, so I will slow down while I do that at the same
Well, we can
time.
add it to the recordings so that it makes sure it gets through. But I'm thinking for the slides is takes like this one with the formulas on it, maybe a handful of the other ones. You certainly don't need all the animations and all that stuff, but I
Yeah,
think
sure.
where the uniform distribution along the reliability vertical axis, I think
Mm,
two slides, there's like that key point of no matter what distribution you're using, it turns into a uniform when you start with the reliability 0 to 1.
mm.
Because I think that's what makes this inverse distribution stuff possible.
Yes, the RAND um,
We ran a
function or
uniform
formula.
generator, yeah,
Yeah,
random number generator.
and that's and hope, and it's always it's always a challenge to work out what you do and don't include in conversations like this. Can't share it in for whatever reason in the chat. I don't think it.
Yeah, adding anything Microsoft is, to be avoided online. It's just, but I think we can do it through, we use AWS through Amazon, and I think they'll allow you to upload, download spreadsheets. So I think we should be in good shape there.
Either way, I'll one way or another, Fred, I'll get this demo spreadsheet to you.
All right.
And of course, it's already set up. You can change the parameters and have a bit of fun. Fun's a strong term, I know. But and of course, it's not just switching systems. You can actually use Monte Carlo simulation to model series and parallel systems where the system fail, like series systems, the system fails in the first component fail. So you simply find the minimum time to failure for series system, and for parallel system, it fails in the last component fail. So you find the last or the highest maximum time to failure.
One of the things that's difficult with this, Chris, is finding the underlying distribution for those various components or
Of course,
subsystems in it. That doesn't go away. That's still some engineering work there.
that's a Weibull analysis webinar that will help people find those reliability curves
Yep. I think we've done that before. You've done it. Yeah.
once or twice.
Yeah. Yeah. All
But
right.
yeah, more than happy to share these demo spreadsheet, and I'll get something going with the slides.
Well, we'll have the recording for the slides as the minimum, but we could add just the
Yes.
formulas to this, like to the text part of it so that they're available.
Yep.
Make it
Absolutely.
easy. All right. So Mike's asking a question in the
Is
questions
he?
tab. Yeah.
Yeah, to get the spreadsheet.
Oh, there he is. Yeah, he's asking for spreadsheet also.
Yep. Yeah,
Yeah.
I think we're good to go.
I don't know. We got two requests. Maybe we could charge $1.99 for it.
That's true. Oh man. So it's $3.98.
There you go. All right. Well, I think you've just blown the audience away here. And
Hopefully in a good way.
yeah. No, I think it's cool. I think we're in good shape.
But I think the main point is, look, you're not supposed to walk away from here again being a master. There's no way. There's no way. Oh, thanks, Sebastian. It's just to understand the art of the possible and hopefully see that it was relatively simple for me to do this, and I'm familiar with it. So there's no reason why any of you people can't also become do this relatively simply as well. Is just understand the building blocks, and of course, you need to go polish your skills thereafter. So the main takeaway is it's Monte Carlo simulation is nowhere near as challenging as it might sound. It can solve or analyze really complex systems in a very structured way. If you need more accuracy, you increase the number of simulations. And even though poor old Excel took a while to chug through 10,000 simulations, there's no reason why you can't do 100,000 simulations. It might need to sit there for 5 minutes, but that's fine. If in 5 minutes you just go have a coffee or go, you know, have a chat with someone, go read a book, 5 minutes to get a really robust CDF curve, that usually is going to be an investment well made. But yeah, the main point is it is quite simple when you try and do it yourself, if you know how to do it. And it can, yeah, you should never do things like assume the perfect switching system where the switch is always going to work. Otherwise, you'll miss that really important first little hump in our histogram where our system fails when the primary pump fails. And that's obviously very important if the L10 life in particular is a very important metric for you guys, because if in this case, I think about 20%, 30% of systems failures occurred when the first pump failed, when the switch didn't work. Well, a perfect switching system model wouldn't have covered that. And you could have saved yourselves millions of dollars in damages or whatever consequence of that poor decision you might have made incorrectly would have been if you didn't model it properly. No, as I'm seeing some good feedback. I see that Edward says it's a lot for you to digest, which I appreciate. Again, it's just there to tickle the fancy, show you what you can do. And of course, maybe I might do a Monte Carlo course in the future. Oh, one of your favorite webinar topics, Kevin. Thank you very much. I was hoping that one day I'd get to the lofty heights of one of your favorites, but finally cracked that glass ceiling. Thank you very much.